Good evening, everyone, and welcome back to the tutorial 10 of surface water hydrology. So, in this lecture, we are going to deal with the problems related to the flood frequency analysis or frequency analysis in hydrology. The video lectures have been already uploaded, and you may have watched the videos. So, I will give first some brief uh, introduction related to the topic, and then we can proceed with the problem set. So first of this all, for the frequency analysis, so in this topic, we are going to deal with the mostly with the return period that you may have read in the last few lectures. So let's say there is this is the time series of discharge with time, and let's say this is the threshold. These are your flood events. So the time difference between the two extremes, or let's say I may say, let's say there's an hydrological extreme at T1. So after how many days or how many years the same event is going to happen. So we call that as return period. And in this frequency analysis, we are going to estimate this return period and the corresponding discharge also if our return period is. But before going into the frequency analysis, there are some basics about probability and statistics. So one of the thing you may have read is probability mass function or PMF. So probability, let's say we have a random variable in which we have x1, x2, x3, and xn. This is our x, where x is the random variable, and these are the events in the random variable. Then the probability mass function of x, random variable x, can be represented p of capital X, small x, where small x is an event. So there are some properties of this probability mass function. One, you may know that probability is always greater than equal to 0. Second is that if we sum all this probability mass function values corresponding to all the xi's, then this gives us total probability, which is going to be 1. And then you may have read about cumulative distribution function, which is the CDF. So it's defined as f of capital X, small x, which is that probability x such that x is less than xi, and this can be represented as summation of e x equal to xj, where j is j is running from 1 to I. So then this probability mass function is related to your discrete variable. Now if the variable is continuous, then you have probability density function. And the probability density function is represented as small f of capital X of fx. This should be greater than 0 as we had in probability mass function. And the second thing is that if we integrate, just like in the probability mass function, we took the summation, then your value over this integral from minus infinity to infinity should be 1. And similarly, the CDF in this case, if you have capital F of x, small x then your P should be, this means that probability capital X is less than small x. You can take xi or x, then you can have to integrate this up to x minus infinity dx. So we will start with the problem one. That's we have to evaluate the constant a for the following expression, which is to be considered as probability density function, where p of x is ax square and x belongs to 0 comma 5. Now the question is, what's the probability that a value that's being selected at a random from this distribution will be less than 2? So the question first is probability x is less than 2. Second is that probability x is falling between 1 and 3, that's it's greater than 1 and less than 3. The third part is probability x greater than 4. Then we have probability x is greater than equal to 4, and E, which is probability exceeding 6. So first of all, I think what's important is the in the equation we have unknown A. We are going to first compute A. So from the definition of the probability density function, that if you take the whole integral of this probability distribution function over an random variable from minus infinity to plus infinity, or the value over which it is being defined, or the interval, the value is equal to 1. So it means integral of p of capital X small x dx from minus infinity to infinity should be equal to 1. Since the probability of x small x is 0 except when x is greater than equal to 0 and less than equal to 5, so this integral becomes 0 to 5 p of capital X small x dx equal to 1. Then we can put the value. This is ax square dx equal to 1, which implies that ax cube upon 3 from 0 to 5 should be equal to 1. So if you put the limits, this is 125 upon 3 minus 0 cube divided by 3, which is equal to 1. Then a will be 125 upon 3 equal to 1. It means a is 3 upon 125. So now your probability function is actually 3 upon 125 x squared. Now we are now going to estimate the values of the probability for the first part, for the second, third, fourth, and similarly for the fifth. So in the case of first, so probability x is less than 2, so it means you have to integrate from minus infinity to 2 p of x small x dx. But you know that p of x is defined over 0 to 5, so the integral gets reduced to 0 to 2. Then you have the value of a, which is 3 upon 125 x squared dx. So to solve this, it becomes x cube upon 3 over 0 to 2. So this becomes 125 upper limit minus lower limit. So it will be 2 cube, which is 8 divided by 3. So this will be 8 upon 125. So this is the probability corresponding to the random variable when the random variable is less than 2. Now the second is that you have x lies between 1 and 3. So whenever you have to find the probability between two limits, it's very important that since x belongs to 0 5 to 5 and 1 to 3 is a subset that's belonging to 0 to 5, then you can directly take the limits 1 to 3 p of x dx, and this becomes 1 to 3 upon 125 x square dx. So this is 3 upon 125 cube upon 3, 1 to 3. So if you solve it, it becomes 8 upon 3 minus 1 upon 3. So this is 3 upon 125 into 7 by 3. This will go, and the value is 7 upon 125. So this is the probability which is corresponding to the value of x when x is greater than 1 and less than 3. Now the third part is that you have to find the probability that x is greater than 4. In the similar case that you can do is this will become 4. Since it's greater than, then you have to take infinity p of x small x dx. Since x limits to 5, then this integral reduced to 4 to 5 p upon 125 x square dx, and this is 3 upon 125 x cube upon 3, 4 to 5. So 3 and 3 will go. So this is 125 if you take upper limit minus lower limit. So this is 5 cube, which is 125, minus 4 cube, which is 64. If you do the calculation, this is 125, 61, which is 61 upon 125. So this is probability corresponding to when x is greater than 4. And in the fourth part, it's been asked that if this would have been equal to 4. So in that case, since it's a probability density function, not probability mass function, so equal to will not change the value, so it will be same. So in case of probability x greater than equal to 4, the probability will remain same, which is 61 upon 125. Now in the case of fifth problem, which is probability that x exceeds 6. So you can directly say the value because your x belongs to 0 to 5 for this, so it will go to 6 to infinity probability of x dx. Since probability is not defined for 6 to infinity, since it's been defined to 0 to 5, so the value will be 0 here, and the probability that x will be greater than 6 will be 0. Uh, any problem till now in this question? So if not, then the other important thing in probability is, or the statistics is the expectation. Expectation, or I can say better to use, is the method of moments or moments. So moments here is similar to how you were calculating the center of mass during your 12th grade or 11th grade. So let's say you had these masses, and at some point you used to take the distances and the mass, then took the summation of these mixi divided by summation of mi's. So in the same analogy, we have moments in statistics and probability. And let's say you have a probability function p of x, which is defined over a random variable capital X. And this is the case of, first let me consider the case of discrete one, then we can move to the continuous one. So let's say we calculate the expectation of x. So expectation is defined that you take the value of x, you multiply the p of xi, and you take the summation of these values for all xi's that you have in the sample. So this is defined as expectation, and this is also called the mean. And similarly, in case of continuous random variable. Let's say you have a variable x which is random variable which is continuous. Then expectation of x, you can write it as, you take the value of x, you take probability density function. It was here probability mass function. This is probability density function. Okay. So this will be also mean, and this is called actually the first movement. These both these are called first movement about the origin. So now let's say you were asked to calculate the second movement. So I can represent that nu2 of x. This would have been nu1 of x about the origin. And then it will be x square f of x small x dx. Now I take the second movement about some point. Let's say it may be mean. I can write it as x bar. Then it will be x minus x bar whole square f of x dx. So this is your second movement about me origin. This is your second movement about me. So any doubts till now? Then we can start with the problem. If not, then let's do a problem which is to find the mean and variance of an probability function which is given. Is a probability density function. It's given a sine 2x and x belongs to 0 to pi. Then it's pi, not n. So we know that that mean, for mean we need to calculate the expectation of x about the origin. This is actually the mean, and this is given. We found it as x p of x dx, and in which interval it is found defined, which is 0 to pi here. So you can solve this. This is 0 to pi x into a sine of 2x dx. Now you can take the a outside. This is 0 to pi x sine of 2x dx. Since we have two functions here, we can integration it by parts, keeping x as such, then integrating sine of 2x minus, we need to differentiate x, and then you need to integrate sine of 2x. After this, you need to put the value of 0 to 5. So this is a, x will remain as such. This is not here, this is just 0 to 5. You have to put the limit over all this function. So integral of sine is minus cos of 2x divided by 2, 0 to 5. Even the differentiation of dx, x is 1, and the integral is again cos of 2x divided by 2, and this will be minus. Then you have to integrate it again. When you put the value of upper limit, so upper limit will be here pi, so minus you can keep outside. It's better to keep minus here. This is cos of 2 pi divided by 2, minus you put the lower limit, so x is 0, cos of 2 0, here 2 into 0. Then here you have integral of cos, which is sine, then minus minus will become plus. So this is sine of 2x divided by 4, 0 to pi. And if we solve this, so cos of 2 pi is cos of, sorry, so cos of 2 pi is 1. So this is going to be a into minus pi by 2. So this will be 0, and then sine of 2 pi is 0 and sine of 0 is 0. So this is going to be 0. So your mean is going to be minus a pi by 2. And now for the variance, one thing is that here that the a is unknown to us. We can also compute a by the definition of probability mass function or probability density function here. So that's from minus infinity to infinity. P of x, small x, dx is going to be 1. So if you put the values, this is going to 0 to pi. A sine of 2x dx is going to be 1. So which implies that if you integrate this, so this is going to be minus cos of 2x divided by 2, 0 to pi is equal to 1. And now you solve this. So this is going to be minus a cos of 2 pi. Actually, no. The a is here 5. Sorry, I wrote question incorrectly. So here it's minus. So this is going to be minus 5 into pi divided by 2, which is equal to 5 pi by 2. Ignore this part. And second thing that we are told to calculate is the variance. So variance is defined as the second moment about mean. Now important thing is that so variance sigma square is going to be expectation x minus mu whole square, and this is expectation of x square minus expectation of x whole square. So this we have already calculated. We need to calculate is expectation of x square. So expectation of x square will be x square uh, p of x dx from 0 to pi. So this is going to be 0 to pi x square sine of 2x dx, and a is there. Again, we have to switch to the integration by parts. So this is going to be a into x square minus cos of 2x divided by 2 minus, then differentiation of x square will be 2x minus cos 2x upon 2 dx. So this is going to be a, so this is 0 to pi. This is going to be pi square minus pi square upon 2. Then you have minus, you need to solve this integral, which is x cos of 2x dx. So you have to solve this by parts. So 0 to pi. So this will be x sine of 2x divided by 2 minus the differentiation of x will be 1, and then you have integration of cos 2x, which is sine 2x dx. This will be 0 to pi. This will be a minus pi square upon 2 plus. So this upper limit will be sine 2 pi, which is going to be 0. lower limit is sine of 2 0, which is also 0. So this term will overall become 0 minus. So integral of sine 2x is minus cos of 2x, minus minus will become plus, divided by 4, 0 to 5. This will be a minus pi square upon 2. Cos of 2 pi is 1. Yeah, so cos of 2 pi is 1, and similarly cos of 0 is also 1. So this will be minus a pi square upon 2. A, we know it's minus 5, so minus 5 minus minus will be plus 5 pi square upon 2. Now important thing is to calculate sigma square. You can put the values back. So this is 5 pi square upon 2 minus your expectation value was 5 pi by 2, which is 5 pi by 2 whole square. So this is 5 pi square by 2 minus 25 pi square by 4. So if you calculate this value, so it is going to become minus 15 pi square by. Any questions in this? So I think there is some problem in the formulation of this problem. But yeah, this is the actual method through which you have to compute the mean and variance. So now we are going to start with the problems on return period. As last time defined, the return period, which is capital T, is defined as 1 divided by probability that x, which is your given discharge, exceeds some threshold xt. So in this problem, you have to assume that the return period of 3000 cubic meter discharge is 6.25 years, and we need to determine that the probability for the annual maximum discharge to be equal to or exceed 3000 cubic meter at least once in the next 5 years. So T is given to be 6.25 years, and probability of exceedance, which is T x greater than xt. Here xt is your 3000 value, is equal to be 1 by t from this equation. So this is going to be 1 divided by 6.25 years, and the value is going to be 0.16. Now we know the probability that annual maximum discharge will never exceed in 5 years is going to be equal to be 1 minus p 4 is power 5 times. So if you put the value, this is 1 minus 0.16 4 raised to power 5 is equal to be 0.84 times 4 raised to power 5, which is equal to 0.41. So, but the problem was to calculate the probability of discharge to be equal or exceeded at least once in the next 5 years. So that will be to exceed at least once in 5 years is going to be 1 minus the probability that the annual maximum discharge will never exceed in 5 years. So let's say you represent this probability by some value of capital Q, then it will be 1 minus capital Q, which is 1 minus 0.41, which is equal to 0.5. So you may wonder how this has come up suddenly. So this is actually a problem related to the binomial distribution, if you remember. So let's say you have probability that x is equal to 5, or probability of, I can say a probability of success or failure, where success is that you are exceeding the limit and the failure is that you don't exceed the limit, and you represent that by NCR, P raised for R, Q raised for N minus R. So this is the probability that event is exceeding. If you take the summation of this R running from 1 to N, you get a total probability of 1, and this is how you compute now the probability in this case. And similarly, in the problem number 4, if the exceedance probability of a particular flood is 1 by 30th of its non-exceedance probability. Now this exceedance and non-exceedance probability, as I said, it's just like failure and success. So if there is a failure P and there is a success Q, then the total probability of these two will be 1. So if you know the failure, you can compute the success, and then find out its return period. You need to compute the return period, and you know the return period is related to P, which is 1 by T, which is the success here, which is the exceedance probability. And also we need to find the probability of such an event occurring exactly once in 5 successive years. So now this is what I was telling, the binomial distribution. So you have now the success of 1 in 5 years. So this means that during 5 years of period, exactly once this limit is going to be exceeded, or there will be a success. So by definition, we know that P plus Q is equal to 1. So this is probability of exceedance, and this is probability of non-exceedance. So the first thing is to compute the P and Q. We are given one more relation, that probability of exceedance, that's P, is equal to 1 by 30th of probability of non-exceedance, which is Q. So if you use, this is equation 1, this is equation 2. If you use equation 2 in equation 1, you have 1 by 30 of Q, or you can write this equation as 30P equal to Q. So if you substitute the value of Q in equation first, you can write P plus 30P equal to 1. So P is 1 upon 31 and Q is 30 upon 31. So the probability of non-exceedance is very high and the probability of exceedance is very low. And you can divide this, you can find this is 0.032 and this is 0.968. Now the thing is that we know that return period, I can write here, which is defined as T, which is equal to 1 by P, where P is the probability of exceedance. So this is T is equal to 1 by 0.032. You compute this, you get a value of 31 years. And we can see from here only the inverse of this, or if you take the denominator, this is 31 years. So the question, or second question, is that we need to find the probability that the event will occur exactly once in 5 successive years. I said it is more related to the binomial distribution, which is NCR, P raised power R, Q raised power N minus R, where P is your success, Q is your failure. So you need to find that, let's say your N is 5 and your P value is 0.032 and your Q value is 0.968. So this is going to be 5C1 because there is one success, then P will be power 1 and Q will be 5 minus 1. So which is equal to 5C1, P raised power 1, Q raised power 4. So 5C1, you know, NCR is n factorial upon n factorial into n minus r. Sorry, r factorial into n minus r factorial. So 5C4 will be 5 factorial divided by 1 factorial into 4 factorial, which is 5. So this is 5 into, you put the value of P, which is 0.032, into the value of Q, which is 0.968, whole to the power 4. So if you compute the value, it will be 0.14. So the probability that an event will exceed once in 5 successive years, given that it has a return period of 31 years, is 0.14, around 14% of probability. Now we can move to the frequency analysis, which is the main topic where we can now start. So in case of frequency analysis, so this is used to estimate this return period. And in the frequency analysis, I can broadly categorize this into two methods through which we can do it. One is the non-parametric, another is the parametric. So non-parametric, you can understand that there are no assumptions related to data or the distributions. Here we have some assumptions in case of parametric, which we are going to see in further slides. So yeah, in this there will be a general equation of frequency that's going to be used. Non-parametric, you can understand, it's more like a graphical method. And this one is bit a probabilistic method. So yeah, in case of, I will start with the non-parametric one. I think we have covered in the previous tutorial this one. So in this, we have plotting position formula. So what you actually do is you take the data, you sort the data in decreasing order, then assign a rank, and then from that rank you compute the probability of accidents. But now the important thing is the computation of accidents, where these two things remain mostly common. So there are different formula that has been given for this. One of which you may have heard of is the Weibull formula. It's very famous one. So other things, other formulas, I will put them here, but we are going to do the problem on Weibull. And one is California, and that probability is defined upon the rank. M is the rank, N is the total number of data that you have, data points. Second is Hazen, which is P is defined as M minus 0.5 upon capital N. Wibble is defined as P equal to M divided by N plus 1. Similarly, you have other methods. I will just mention these three here. And now the important thing is our focus is not only on the probability of accidents, our focus is on the return period. So once you compute this probability of accidents, you know that probability of accidents is, which is x greater than xt, is actually 1 by the return period. So once you compute this probability of accidents, you can take the inverse of it and you can get the return period. And the plot that you are going to generate for this, that's the discharge versus time. So this is called flood. You can see plot. So any doubts till now in this part? So if not, then we can move to the problem. So in this problem, you are being told to consider the annual maximum discharge data at a river gathering station over a time period of 40 years. You need to construct the flood frequency plot first and then estimate the following. First is the flood magnitude with the turn period for 10 year, 50 year and 100 year. And the other thing is to estimate the return period of a flood with the magnitude of 4000 cubic meter. And I think, so this is the table. You are given the year, flood discharge, similarly year, the flood discharge, year and the flood discharge. For this, I will share the Excel sheet. So yeah, this is your flood discharge, and these are the values that are given in the problem. So the first thing is you have to sort these values in decreasing from the largest to the smallest. The next thing what you have to do is to assign a rank. So the highest value will be getting a rank 1, and second, after this there will be second, then third, and so on and so on. So till you reach, so you have 39 values. So the probability will be defined as m divided by your capital N, which is 39 plus 1. You compute the probability of accidents. Then you compute the return period, which is 1 divided by this probability of accidents. Sorry. Now the important thing that we need to do is to construct the flood frequency plot, which if you recall, I said it's a plot of discharge versus return period. If we take this as x-axis and the discharge on y-axis, so on the x-axis we can put the return period, and on the y-axis we can plot the discharge values. Yeah, so important thing here to note down is that if you see this is a nonlinear relationship, and by applying the logarithm, I think we can obtain the linear relationship, and that can be obtained by taking here log. Let's say I take log 10 of this number, which is the return period. So this is log of return period, and now we can change the x-axis and see whether we could get it. Now you can see that we have a linear relationship where on the y-axis we have the discharge, on the x-axis I have plotted logarithm of return period. Now we can add a trend line, a linear trend line, and now we need to determine the equation of this trend line. So any doubts till now? Because now this equation will be very important for us. We can now, so let's say I need a discharge, or I need a return corresponding to some return period, I need some discharge value, or I need return value corresponding to some discharge, I can use this equation directly because all the points lie nearly on this equation which is fitted to these data points. So if you remember, we got the equation y is equal to 3869 of log of return period, which is 10 plus 1391. Now, if you go back to the problem, what was asking, so constructing the flood frequency plot, which you have done. Now, the second thing is to compute the flood magnitude with the return period 10, 50, and 100 years. So, the first thing is to compute y10, which is that when the return period is 10. So, this is log 10 of 10 plus 1391. So, if you compute this, give me a second. So, this will be 3869 plus 1391. So, this is going to be 1. So, this value will come 5260. In the second, you are being asked to calculate y50. So, this will be 3869 log of 10, 50 plus 1391. So, log of 50 is 1.69 plus 1391. If you compute this value, so this will be 7929. Similarly, if you compute the value for y100, this will be 3869 log of 10 of 100 plus 1391. We know 10 of square is 100, so this is 3869 into 2 plus 13691, which is equal to 9129. So these are your three discharge corresponding to three different return periods. So there is another part of the problem, which is to find a return period of flood with a magnitude 4000 cubic meter. So you know now you know why. So in the fourth part, y is known. Y is to be 4000 cubic meter, and you need to determine t. So this is going to be, if you put the values in the equation, 4000 is equal to 3869 log of 10 of t, which is plus 1391, If you solve this, this will be 3689 log of 10 of t equal to 4000 minus 1391. So this will be 2609. So if you calculate log of 10 of t, so this will be equal to 2609 divided by 3869, which will be equal to 0.67. So t will be 10 to the power 0.67, which will be equal to 4.67 years. So this is going to be the return period for the discharge of 4000 cubic meter. So these are this problem was dealing with the non-parametric method in which we used the Webble's formula to determine the return period and also the flood magnitude corresponding to different return periods. So any doubts till now? If not, then we can move to the parametric ones. So in case of parametric methods, I will, in this tutorial, I will cover the normal one, normal distribution. Second will be log normal, and the third will be log Pearson tree distribution. So for any parametric distribution function, if you have to determine the magnitude of x corresponding or magnitude of the discharge or the flood corresponding to some return period, so it will be given as x of t equal to x bar, which is the mean, plus ks. So this will be the mean computed from the data. This will be frequency factor, and this will be standard deviation. Now, taking the case of the normal distribution, so a standard normal distribution looks like this, where it has no CQNS, and if you compute the standard Z square for this distribution, it will be xt minus x bar whole divided by s. And let's say this Z lies here, then this area is called the exceedance probability, which is 1 by t, and this portion is called 1 minus 1 by t, which is non-exceedance. What you need to do is to estimate the Z score from the normal distribution, standard normal distribution table. Or you may know the Z square and you have to calculate the probability, or if you know the probability, you can compute the Z score from that Z score from that table. Now we can do a problem on this, which is using a normal distribution, using the same data that we had earlier in the problem where we use the non-parametric one. And we need to compute the flood magnitudes with return period 10 years, 50 years, and 100 years. The data remains same. So what important thing we first need is the mean and standard deviation of the data set. I think I can share that and we can compute in that. So this is your flood discharge data that is given. So the first thing is to compute the mean. You take here. So mean is computed by taking average. And similarly, you can compute the STD, standard deviation of sample, which comes equal to 1475. So if I write your X bar is 2995 and your sigma becomes equal to 1475.15 is 0.97. So important thing is first is that the problem that is here is that you need to compute a flood magnitude corresponding to 10 years. So we are given that the return period is 10 years. So probability of accidents, sorry, is 1 upon T or 1 upon 10, which is equal to 0.1. And the probability of non-accidents, which I can mention or which I can write here as P of X less than X10, that will be obviously 1 minus 0.1, which is 0.9. Now the important thing is that let's say we want to find the, if we are know the probability of accidents, then we want to compute the, for non-accidents we want to compute the Z score. So since I am not having here Z table or the Z score table, I will mention the values. So let's say the table is going to be like this. So from here you may have probability values, and from here it may be Z square values. So for an probability of let's say 0.9 that we have non-accidents, so we are going to compute Z score. Since in the table you won't find the value, exact value corresponding to 0.9, so you will have a value less than 0.9 and greater than 0.9. So one less than, the value less than 0.9 will be 0.899 in the table, and greater than 0.9 it will be 0.9015. So the Z1 corresponding to this is 1.28 and the Z2 will be 1.29 from the table. So we can now linearly interpolate between these 2 points. So let's say you have P1 Z1, P2 Z2, and you need to compute Z here, given that you know the probability. So the probability is known to be 0. So you fit a straight line between P1 and P2, then you can estimate the value for here. So I will write the equation, which is Z is going to be Z1 plus Z2 minus Z1 upon P2 minus P1 into P minus P1. So if you put the value, this is 1.28, 1.29, it's 1.28 divided by 0.9015, 0.8997, 0.9 minus 0.8997. So if you solve this, this comes equal to 1.828. Now the important thing that is we have computed the value of Z, not the value of flood magnitude. And for the flood magnitude, if you remember, I just said that xt is given as x bar plus k times s, where this is frequency factor, which is here z, and this is variance, and this is mean. So xt will be, your x bar is 2986, sorry, 2995, plus your k is 1.828, and your s is 1475. If you take the value here, it will be around 4857. So this is going to be your discharge corresponding to 10-year return period. So any doubts till now? If not, then we can similarly compute for 50-year return period. For 50-year return period, your P will be 1 divided by 50, which is going to be 0.02, and the value of Q or P x less than xt will be 1 minus 0.02, which is 0.98. And if you estimate the Z from the table, it will be roughly 0.2.04. And therefore x50 from the same equation that we used earlier will be x bar plus I think the notation was k times s, and your x bar is 2986 plus your value of k is z, which is 2.054, into your value of s is 1458. So this will roughly come out 2981 cubic meter. And for 100-year return period, your P will be 1 divided by 100, which is equal to 0.01. And your probability that x, so this one is probability x greater than xt, this is less than xt, this is going to be 1 minus 0.01, which will be equal to 6377 cubic meter. Sorry, this will be equal to 0.99, and the z value will be, in this case, will be 2.326, and if you estimate x Henry, this will be 2986 plus 2.326 and 1458. So this value will come to 6377 cubic meter. Any doubts still now in the problem? So if not, then we can go to the law of normal distribution. So this distribution is actually a normal distribution if you just apply a log to your data, and once you apply the log, the distribution becomes a normal distribution. And if you want to calculate the mean, in this case it will be 1 by 2 ln x bar square upon cv square plus 1. Similarly, your sy is going to be ln cv square plus 1. So y bar comma sy, these are your mean and standard deviation of transformer data. And x bar cv are mean and coefficient of variance of x, actually of your actual data. I can say not x, actual data. And the cv can be computed by sx upon x bar. And now the equation will become yt is equal to y bar plus ky sy. And once you find the yt, xt can be represented as e raised to yt because you have applied a logarithm. Or we can do the same problem that we did on the normal distribution. We can do it by the log normal distribution, and we'll try to estimate the return period for 10, 50, and 100 years. So this is your flood discharge. We can take the logarithmic of the data set, and then we can compute the mean, just like we have computed here. We can compute the standard deviation. I think these two are sufficient. We don't need the coefficient of variance here. So mean is going to be 7.89 and your standard deviation is going to be 0.48 once you apply the logarithm to the data set. So in this case now we got a mean of transformer data as 7.89, and similarly your standard deviation is 0.48. So for 10 years return period, your y10 will be y bar plus ky into sy. Now this ky can be found from normal distribution table. And this will come out to be 1.282 that we found earlier problem. So the k will remain same, and the y bar will be 7.89 plus 1.282 into SI is 0.48. So the y10 will be 8.505, and if you want to find the x10, which is log of or ln of y10, sorry, your y10 is ln of x10. It implies that your x10 is e to the power y10, which is e to the power 8.505. The value will be 4939. Similarly, for x50, the value will be 7158, and for x100, your value will be 8156 cubic meter. Now, the last distribution that we need to cover in this tutorial is the log Pearson type 3 distribution. So this is kind of similar to the log normal, so but it is bit different. So in this also you need to transform data. Rather than using natural log, we can take log 10 to the base log to the base 10, and then you compute the transformer mean, standard deviation, and coefficient of skewness. So this is mean, this is your standard deviation, this is your coefficient of skewness. So this coefficient of skewness measures how is your distribution data distribution. Let's say it's standard normal, then your coefficient of skewness becomes 0, and if it is rightly skewed, then your coefficient of skewness is less than 0, and it's left skewed, then the coefficient of skewness is greater than 0. So in this case, xt will be 10 to the power yt, just like in the log normal distribution, this xt was e to the power yt. And this cs you can compute as n divided by n minus 1 into n minus 2 y minus y bar whole cube divided by sy cube. So this is the equation for coefficient of skewness, and we are going to repeat the same problem. Now we are going to use log Pearson 3 type distribution to compute the flood magnitudes with the term period 10, 50 and 100 years. So yeah, one important thing in this case is that just like in the normal distribution or log normal distribution, in these distributions you had a standard z corresponding to which or whose table was given. You had a table, and from that table you computed either z or p, which of these you want to know, and one was given to you. But in the case of log Pearson type 3 distribution, it's a bit different. So here you have a table in which there will be k values and there will be values of cs, coefficient of skewness. So based on the coefficient of skewness and the frequency factor, you are going to, from that table you are going to compute the frequency factor, and from that frequency factor further you can compute the discharge. So this is the same problem. We need to estimate the flood magnitudes. The only difference is now that you have a log normal distribution. Sorry, you have a log Pearson type 3 distribution. This is the last problem, problem number 8. So one of the first thing that we have to do is we have transformed the data into the log base 10. So I will share the Excel. This is okay. So this is log of 10 to the base x, log of to the base 10, and this is your transformer data. So if you want to compute the mean, you can drag it. So this is going to be your mean and this is going to be your standard deviation. You can also compute the coefficient of skewness. The skewness of population. I need the population of sample. So sample. So this is your data. So these are your values. This is your mean, this is your standard deviation, and this is your coefficient of skewness of the data. So I can start. So your mean is 3.47. Your standard deviation is 0.208. Your coefficient of skewness is 0.016. One of the important thing that from the table you are going to find is that you don't have the exact value of coefficient of skewness here. So you take a lower limit and upper limit. When you take the lower limit, you get a value of 8 to be this, and when you take the upper limit of cs, which is 0.1, you get an value of 1.292. So now we can use the interpolation just like that we did in the previous problems. So we can find the value of k, which is 1.28 plus so yeah, sorry for the delay, pause. So your k value becomes 1.292 minus 1.282 divided by 0.1 minus 0 into 0.021 minus 0. So it becomes 1.284. Now y10 can be written as y bar plus the frequency factor into the standard deviation. So your mean is 3.47, your frequency factor is 1284, and your SY is 0.208. If you calculate this value, this becomes 3.2 694, and your x10 is going to be 10 to the power 3.694, which is 493, sorry, 4943 cubic meter. And in this similar way, you can compute the x50 and x100. So this will be 7149 cubic meter, and this will be 8143 cubic meter. So any questions on this? So if not, then we will meet in the tutorial 11 next week. Thank you.